You know, the next generation of artificial intelligence is finally breaking free from those giant, power-hungry data centers. And it's doing it by copying literally the most efficient blueprint in existence, the human brain. Welcome to The Explainer. Let's dive right in.
400 terawatt hours. Just think about that number for a second. That is the staggering estimated global energy consumption of data centers in 2024 alone. It's a colossal, almost unimaginable footprint, and it's largely driven by our current brute force approach to scaling AI.
And this sets up what I like to call the ultimate AI power paradox. On one side, you have the Goliath, right? These massive cloud AI models, fueled by $15 billion funding rounds, churning away inside those 400 terawatt-hour data centers. But then, on the other side, you have David, the human brain. Your brain executes real-time pattern recognition, complex reasoning, and context-adaptive learning on exactly 20 watts of power. I mean, we are pouring absolute billions into cloud infrastructure, yet our tiny 20-watt brains remain the absolute gold standard for true adaptive intelligence.
So, how do we actually bridge this massive gap? Well, here is our agenda for today. We're going to map out the paradigm shift from these clunky cloud networks to sleek, brain-inspired real-world robotics. We'll cover the AI power paradox, decode neuromorphic computing, introduce liquid neural networks, navigate the real world, and finally enter the edge intelligence era.
Section 1. The AI power paradox.
Okay, so the current clock speed ceiling we're hitting in AI, it's actually a fundamental architectural problem. Most current AI runs on the von Neumann architecture, which, believe it or not, was designed way back in 1945. It relies on continuously bouncing data back and forth between a separated memory and CPU. Because of this major structural bottleneck, our GPUs consume massive amounts of energy. I mean, a single NVIDIA H100 draws 700 watts at peak load. At this pace, data centers are expected to reach a mind-blowing 1,000 terawatt-hours of energy consumption by 2030. But more importantly, for actual deployment, this heavy cloud dependency makes true real-time edge robotics practically impossible.
Section 2. Decoding neuromorphic computing.
So how does biology solve this bottleneck? With a totally different approach. Neuromorphic computing completely dismantles that old 1945 architecture by literally co-locating memory and computation across 5 layers. First, the neuron model only fires when it's actually triggered. Second, the synapse model adapts based on timing. Third, the network topology operates as this massively parallel mesh. Fourth, the learning protocol allows for local, continuous adaptation. And fifth, the hardware substrate can span everything from silicon to light-speed photonics. By operating this way, the system draws exactly 0 dynamic power between actions. 0.
The real secret sauce here is found in a specific learning rule called spike timing-dependent plasticity. Basically, it means the connection between artificial neurons changes dynamically based entirely on the exact timing of their electrical spikes. Think of it kind of like the motion sensors in a smart office building. These artificial neurons only expend energy when a specific event actually happens. That entirely removes the need to constantly ping some external server, encoding cause and effect completely locally.
Section 3. Enter liquid neural networks. Now, researchers at MIT took this biological concept and developed what are called closed-form continuous time models, or CFC for short. This is a massive mathematical breakthrough for liquid time constant networks, which are basically systems that constantly adapt to new data over time. In traditional modeling, mapping continuous time meant using really slow, clunky numerical differential equation solvers. But here, the researchers managed to totally bypass those slow solvers by calculating the interaction of neurons precisely in a closed formula.
And the result of that clever little mathematical trick is absolutely staggering. It makes these liquid models up to 5 orders of magnitude faster. We're talking up to 100,000 times faster in both training and inference compared to previous equation-based models. It scales remarkably well while perfectly maintaining that continuous time adaptability we see in biology.
Section 4. Navigating the real world.
Let's look at how this plays out in the real world. In an incredible MIT experiment, researchers trained autonomous drones strictly on offline human demonstrations in a familiar summer forest, the training woods. But then to test their true robustness, they stress-tested these drones in closed-loop flight in completely alien environments. Picture an urban patio filled with tricky adversary objects like bright yellow chairs, totally different lighting, and unfamiliar man-made structures. When you actually map out their attention, you see how wildly different the underlying networks perceive this new environment. The older standard LSTM model, it completely loses the target. its attention map just scatters everywhere, getting super confused by window reflections and background adversaries. But the Liquid network naturally drops all that irrelevant background noise and stays perfectly locked onto the target red camping chair.
This rare ability is known as out-of-distribution, or OOD generalization. It proves that Liquid networks are true dynamic causal models. They're actually learning the real underlying task, which is flying to a specific object, rather than just lazily memorizing the background of a specific forest. They adapt to entirely new scenery in real time.
Section 5. The Edge Intelligence Era.
This aggressive timeline tracks a company called Liquid AI. They're an MIT spinout that took these exact biological principles and packaged them into highly efficient foundational models for commercial use. They were founded in late 2023 and quickly raised $37.5 million in early 2024. Then, by December 2024, they closed a massive $250 million Series A, valuing the company at roughly $2 billion. And looking ahead to June 2026, they plan to release their Liquid Foundation model, the LFM 2.5230M.
And the benchmark scores? They are absolutely wild. Despite its size, Liquid AI's tiny 230 million parameter model completely embarrassed competitors, packing 4 times the weight on structured data extraction tasks. It scored a 22.51 on the case report bench dataset, easily beating Alibaba's 800 million parameter model, which scored just 13.83, and it absolutely crushed Google's 1 billion parameter Gemma model, which scraped together a mere 2.28.
Because it is so biologically efficient, this model runs lightning fast right at the edge. On a cheap Raspberry Pi 5, a computer that literally costs less than a nice dinner out, it manages 42 tokens per second. On a high-end smartphone, it clocks over 200 tokens per second. You can pull complex, structured data from documents instantly without ever needing to ping the internet.
So if this brain-inspired blueprint can do so much with so little, it really begs a massive question. Is the true future of AI locked away in some massive, power-hungry cloud? Or is it already sitting right there in your pocket?